Hey, welcome. Have you ever stopped to think about the universe as just one giant cosmic road trip? Seriously. Every planet, every star, every car, and even you, we're all on a journey. And just like any good road trip, there are rules. So today we're going to grab the map and the keys to really understand the fundamental laws of motion that govern, well, everything.
Okay, so let's just dive right in with a simple question. Are you moving right now? I mean, you probably think, nope, I'm just sitting here. But get this, you're on a planet that's spinning at about 1,000 miles per hour, and that whole planet is hurtling around the sun. This gets us to the very first and maybe most important idea of our whole journey.
And that big idea is that motion is always relative. An object is only in motion if its position is changing compared to something else. So yeah, you're sitting still relative to your chair, but you're moving incredibly fast relative to the sun. See? It all just depends on your point of view.
Now, how do we actually map out a trip like this? When we talk about how far something has traveled, it turns out there are two very different ways to measure it, and in physics, that distinction is a really big deal.
So on one hand, you've got distance. This is the total ground you covered. Every single turn, every detour, the whole scenic route. Just think of it like the final number on your car's odometer. But on the other hand, we have displacement. And displacement is way simpler. It's just the straight line journey from where you started to where you ended up.
And this is just a perfect way to picture it. Displacement is that direct, as-the-crow-flies path. It couldn't care less about that fun little detour you took for coffee. But distance, that's the winding road you actually drove. Now, both are useful, for sure. But for a physicist, displacement is often the one that really matters.
All right, so we've got the map sorted out. Now let's talk about how we actually move along that path. And a great way to think about this is to picture your car's controls. You've got the gas pedal, the brakes, and maybe a compass on your dashboard. These three things correspond directly to our next three key concepts.
First up, speed versus velocity. Now, these two sound like the same thing, right? But in physics, they're not at all. Speed is just a number. It's what your speedometer shows you, 60 miles per hour, that's it. But velocity adds that crucial piece of info from the compass, direction. Velocity is 60 miles per hour north. It's got both a speed and a direction, which makes it what we call a vector.
So what happens when you change your velocity? Well, that, my friend, is acceleration. Now, most of us think of acceleration as just hitting the gas, right? Speeding up. But in the world of physics, it's any change in velocity. That means hitting the gas, slamming on the brakes, or even just turning the steering wheel. Yep, all of that counts as acceleration.
We can even break this down into three basic types. You've got positive acceleration. That's when your velocity increases. You're speeding up. You've got negative acceleration, which we usually call deceleration. That's when you're slowing down. And then there's zero acceleration. That means your velocity is perfectly constant. You're not speeding up, not slowing down, and not changing direction. Okay, so here's a classic physics brain teaser for you. Imagine a race car on a perfectly circular track, and it's going a steady 100 miles per hour. The speedometer needle isn't moving. Is it accelerating? The answer is absolutely yes, because even though its speed is constant, its direction is always changing. And since velocity includes direction, its velocity is changing, and any change in velocity means it is constantly accelerating. Now that we've got all the lingo down, let's get to the man who basically wrote the rule book for motion, the one and only Isaac Newton. His three laws of motion are like the universal traffic laws. They apply everywhere and to everything, from a baseball you throw in your backyard to a planet orbiting a distant star. These are the three unbreakable rules that form the foundation of what we call classical mechanics. First, the law of inertia. Second, the relationship between force and acceleration. And third, the law of action and reaction. Let's take them one by one. So the first law is all about something called inertia. And the easiest way to think about it is that objects are kind of lazy. An object that's not moving wants to stay not moving. And an object that is moving wants to keep moving in a straight line at a constant speed. The only thing that can change this is an outside force. It's exactly why you lurch forward when a car suddenly stops. Your body, thanks to inertia, wants to keep right on going. The second law gives us one of the most famous and powerful equations in all of physics. Force equals mass times acceleration, or F equals m. All this really means is that the more massive something is, the more stuff it's made of, the more force you need to apply to get it to accelerate. It's the reason pushing a shopping cart is a whole lot easier than pushing a car.
And finally, the third law. You've definitely heard this one before. For every action, there is an equal and opposite reaction. This just means that forces always come in pairs. When a rocket pushes hot gas out downwards, that's the action. The gas pushes the rocket upwards with an equal force. That's the reaction. When you push on a wall, guess what? The wall is pushing right back on you.
So how do we actually use these laws? Well, they give us this amazing toolkit of equations. These formulas connect all the concepts we've been talking about. In these, S is for displacement, U is the starting velocity, V is the final velocity, A is acceleration, and T is time. With these three equations, we can predict exactly where something will be and how fast it will be going at any given moment. They're basically the GPS of physics.
Okay, so what happens when all these different objects, all following Newton's rules, actually run into each other? You can imagine it like a cosmic traffic jam. And this brings us to our final huge principle, one that governs all these interactions, the conservation of momentum.
This law is so cool. It states that if you have a closed system, which just means no outside forces are messing with it, the total momentum of everything inside it stays constant. So when two billiard balls collide, momentum might get transferred from one to the other, but the total oomph of the system before the crash and after the crash is exactly the same. Nothing is ever lost.
And that brings us to one last classic puzzle to wrap things up. If Newton's third law says forces are always equal and opposite, then how does anything ever move? I mean, if you push on the ground and the ground pushes back on you with the exact same force, shouldn't you just stay put? Well, the secret is that those forces are acting on different objects. You push on the Earth and the Earth pushes on you. And since you have a lot less mass than, the entire planet, that force is more than enough to accelerate you forward. It's just a perfect example of how all these incredible laws work together to create every bit of motion we see every single day.